Okay, so today we're talking about direct current circuits. So something we've kind of already been working with in the last chapter. The first section here that we get into in this chapter is resistors in series and parallel. This is something that we've already done, and so I'll have just an activity for us to do for this section, and then we'll just move on to the next section since we were already pretty familiar with this. So resistors in series and parallel. So I'll remind you now the rules. If we have a parallel connection like so, with a resistor R1 and R2, and we could have more than just two resistors here in parallel. We could have n resistors in parallel, right? What we want to do is replace these resistors with an equivalent resistor, like so. We'll try to keep things color coded here. So replace these two resistors with an equivalent resistor, which looks like this. It has resistance Req, and the relationship between Req and R1 and R2 is given in terms of reciprocals of the resistance. You may hear the reciprocals of resistances referred to as conductances. But in any case, what you do is you sum up. Well, we don't have to write a summation for this little number of resistors. It's the sum of the reciprocals. So it's 1 over R1 plus 1 over R2 is equal to 1 over Req. Now, there's an alternative formula you can use when you have only two of these resistors in parallel, and that is the product over sum formula. So the product on top, so R1 times R2, and the sum on bottom, R1 plus R2. And so these rules work for parallel only. So this is parallel. Okay, parallel combination.
Professor, can you do this with more than one, or is it only for two?
The top formula will work if you have n resistors. The bottom formula is very inefficient if you have more than two. So I only present the formula on bottom for the case of two resistors. If you have three resistors, it may be faster for you to do product over sum and then do product over sum again. So you can always replace two resistors with one resistor using the product over sum formula. And then since you go from 3 to 2, then you have 2 again. So you can do product over sum again. And that's usually faster than summing reciprocals, because in the calculator, when you get your final answer, you have to reciprocate your final answer. Okay? So that is parallel combination. Let's take a look now at series combination. So two resistors in series looks like this. So here's an R1 and here's an R2, like so. And we want to replace these two series resistors with a single resistor, namely the Req resistor, like so. And the way we do that is the equivalent resistance that replaces R1 and R2 is simply equal to the sum of the resistances of those two resistors. So R1 plus R2. You probably have noticed already, you've done a lot of problems on this, that resistors and capacitors are kind of opposite in terms of the formulas that you use, right? So capacitors in parallel add, but it's resistors in series that add. Capacitors in series, it's 1 over the reciprocal to get the equivalent, and for resistors in parallel, it's 1 over the reciprocal to get the equivalent. So capacitors and resistors are opposite in terms of which formulas you use for parallel and series. So this is a series combination only. All right, so the bottom formula for 3 is something like R. Yeah, so it's a pretty nasty formula. So you don't want to use it. Yes, exact. So you can just do the reciprocals, or you can apply the product over some formula twice for 3 resistors, and sometimes that's pretty quick. Remember, I gave you guys an exercise where we looked at the case when the resistance values for resistors in parallel were the same value, and you see that you end up with like 1/3 of the overall, sorry, the equivalent resistance is 1/3 of the value of one of those resistors. So use tricks like that to kind of recognize quick combinations to save yourself time. Okay. So those are the parallel and series combinations. So now I have an activity for you guys to work on. And this is not any particular activity that's included in the book. This is just a typical lab activity that you might do for maybe like a pre-lab or something like that. But it's quite a fun one. So I'll actually put you guys in rooms with each other to work on it together. So you're given 4 resistors. So you have 4 resistors with resistance R for each of those resistors. So they're identical resistors. Determine the equivalent resistance for every combination and there's 10 combinations. Okay, so what do I mean by this? Well, what you do is you imagine you have these 4 resistors and you start connecting them in various ways. So I'll just give you the first 2 very simple ones. So number 1, connect all of the resistors in series. What do you think number 2 is going to be? Right? Connect them all in parallel. Okay, and so your task is essentially to change these connections until you've gotten all 10 combinations and determined all of their equivalent resistances. So each of these has a resistance R, 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 R. And I'll go ahead and give you maybe one more just to get you kind of started on how to figure these out. Well, I have here 4 resistors in series, 4 in parallel. So now I need to start looking at 3 in parallel with 1 in series, right? Or 3 in series in parallel with 1. So that would be like the next thing to take a look at. So for 3, maybe something along the following lines. I have 3 of these guys in parallel. And then I have, finally, that one is now in series with this one. And all of your answers for REQ will be given in terms of R. Okay, so some fraction times R, some number, right? So We're looking for REQ. So does anybody have any questions about what we're doing before I put you guys into your groups? You can work, with partners and stuff to kind of figure this out. So it's actually a pretty fun activity once you get working on it. It's kind of interesting to see all the different kinds of combinations you can make with just 4 resistors. I just want to tell you that there's 10 because some people might think they found all of them when they get 7, and then they might stop there. So there's definitely 10 combinations. So are there any questions?
Yes, so we need to find the rest of the 7 combinations.
Yes.
Okay.
And then find their equivalent resistance.
Okay, got it. Thank you.
Okay. Just to be 100% clear here, what is the equivalent resistance of the combinations which are here already, or at least the first 2? Well, this one is going to be 4R, right? And then this one is going to be R over 4. Okay. All right, so let's go ahead and if you can't find them all, well, I'll come around and I'll help you, right? So that shouldn't be a problem. I'm going to go ahead and break you guys into the rooms now. I'll give you about 2 to 3 participants per room, okay? And just assign automatically. Okay, the rooms are open, so go ahead and jump in. Andrew and John, you guys here? John? John, are you there? Juan, let me go ahead and give you an assignment here for the rooms. Can you hear me?
Yeah, I went to fix my mic and it made me leave the Zoom.
Oh, okay. Which group which one
I
were
think it
you
was
in?
room 1
Was room 1?
with
Um,
Brandon and
okay, I see room 6 only has 1 person though.
I think
Um,
it was 1.
okay, but I'm gonna put you in 6 because he's all by himself, okay?
Okay.
It's the other Juan Diaz. Hey, Juan Diaz. So there's two Juans here. So um, I will. Did you were you just asking because you were by yourself in here, or okay, yeah. So now you have another partner here to work on it with. I'll come around here pretty soon, just giving everybody some time to get started on it. Do you understand what's going on? Okay, awesome. John, can you hear? Are you there? Join your breakout room if you're there. Hello. Do we have any questions here?
Yeah, actually, I had one question. Um, so all the resistors are the same, like resistance, right?
Mm-hmm.
Okay, and then we're just like solving in terms of R.
Yeah.
Okay, okay,
So it's just going to be some fraction times R, or some number times R.
okay, cool.
All right.
I think that
Do
was it.
you have any questions? Jiho, do you have any questions? Okay, I'll just take that as a no.
Looks like
Here
a
we go.
box of
Recording in progress.
Hello. Do you guys have
Hello.
any questions?
Um, Actually, I do have a question. I have one where it looks like have you seen the one, Professor, the diamond one? The one
Uh,
that looks like a diamond?
yeah. Are you talking about like a Wheatstone bridge?
I don't know what a Wheatstone bridge is, but in the book there's one that looks like a diamond, but
Yeah.
it has a resistor in between, but I just took out that resistor.
Yeah. So yeah, probably the best way to draw it without the resistor in the middle would be something maybe like this. I can just share real quick.
All right.
Um, like something like this with the two resistors like this. Is this what you're talking about? So it's just these ones are in series and it's in parallel with these other two. The Wheatstone bridge is the one where you have, or excuse me, there's a galvanometer here.
Well, I was thinking something like this.
Mm-hmm. Yeah, that's
Or is
that's
it the same thing?
That's identical. Yeah. Because
What about something like this? Hold on, Professor.
okay.
How about something like this? So kind of where I have the scribbles, that's where the resistor is. So I have something like this. So this one's in series. This one right here is in series. And then these three are kind of in a diamond shape. Does that work or no?
Yeah, so you want to be a little bit more organized. Don't draw like kind of like this, these kind of shapes. This is kind of what you're talking about, right? So you have two up here maybe, and then one over here.
Yeah.
So the way I would draw this is like this. I would draw it kind of like in a block. Like that.
Okay.
Just to keep it nice
Let me
and
see.
kind of understandable, so to speak. It's like we know these two are in series right here, right? And we know that those two are in parallel with this one, and we know that these three are in parallel with this one. Make sense?
Mm-hmm. Oh, okay, okay. So I have one that is pretty much the same because I have two. I have one that's like a diamond with the four resistors, and I have one just like the one you wrote. So I'm gonna just remove that one.
Okay. Anybody else have any other questions? Andrew, Hillary?
No, I'm good. Still drawing.
Okay. Andrew?
I don't have any questions.
Okay. I'll go to the next room. Hey, do we have any questions here?
I'm not quite seeing where you're getting 10 combinations.
There are two combinations which are identical, but in just from a connection standpoint, you can put it in terms of like you probably. So, are you talking about that?
I did find the two that have identical resistance, but I still only found 9.
Well, you would have to show me. So maybe I can do this, and you can write some down. Can you write on this?
Don't think so since I'm in the web version. But
Orphill,
so I had the three from you put down.
are you sure you can't write on it? Orphill was just writing on it a second ago. Maybe there's something I can do real quick.
Yeah, no, it's just I think it's because I'm in the browser.
Oh, okay, got you.
So it doesn't give me the writing tools for whatever reason. But there was basically the 4 in series, the 4 in parallel,
Mm-hmm.
the 1 in series with 3 that are in parallel, the 2 in series with 2 that are in series with 2 that are parallel. So yeah, and then making the 2 on the left there in parallel and then in series with the 2 on the right being in parallel still.
Right.
And then the equivalent one for that, which is 2 pairs that are in series where each pair is in parallel with the other pair.
Right.
Then
These two are identical.
yeah. And then
there's always one that's really tricky, actually. Every
one
time I listen to this.
one outside in series, and then parallel into a 2 split with the top having 2 in series and the other one having just 1. Wait, what?
Like this?
No. Was that the one you're supposed
This is probably the tricky one right here that I just drew.
Yeah, I think that was the one I was missing. Wait, no. Yeah, with all of them in parallel, but only 2 in.
So the one you were talking about must have been this one then?
Yeah.
So this one is like the inverse of this one right here, I think.
Yeah, I think I was missing that 7 there, and then there were like 2 more, which was what? There's a lot here. the one where you have that's sort of like 7, but instead of that 1 2, it's take one of the 2 on the top of that bottom parallel bit and split it off.
Yeah.
Yeah.
This is another one that's kind of gets away from people.
Yeah, I just didn't think of the having 1 1 2 instead of that 7. What was the last one? Oh, we didn't do the one in series with 3 in parallel. I think that's the last
Actually, that was one that you said over here, I think.
Oh wait, no, that was 3.
3 in series with 1 in parallel.
Which one am I missing here?
Like this.
3 in series. Oh, and then yeah, that one. Yeah.
There's 10.
I was just missing 7, which I guess really is. I feel like it'd be easier to draw that just having 3 parallel bars and then having one of them have the
Yeah.
2.
That'd be easier. Same exact thing, yep. David, you getting all this?
Yeah, what I don't we're 4 through 10 on what is that what you were asking also, or just 1 through 3?
Say that one more time.
Because you only wrote down what like the 1 through 3 circuits.
3, yeah,
So you just wanted us to go through the 1 through 3?
No, I want you to go through all 10.
Oh, then where are the other 10?
You're supposed to come up with those yourself.
Oh, my bad.
And that's what me and Sean were just writing down. So you're supposed to come up with these yourself. So please, like, don't copy all of them so that you have something to work on.
Okay.
And then come up with the equivalent resistance for all of these.
Okay.
And then John, finally you're here. Where are you at? Do you understand what we're doing here?
Yeah, I was kind of like, I kind of came midway.
Okay, let me clear this. But you, like David, Sean, feel free to help him out to figure all these out. Let me clear this and explain what we're doing. We have 4 identical resistors. And what we want to do is come up with all 10 combinations. So all 10 possible combinations. And technically 2 of them are like the exact same thing, but we're going to say 10 combinations. And you're looking for REQ. So so all 10 possible combinations for REQ. So the ones that I gave when I first got everyone started was the obvious ones, like 4 resistors in series, right? They all have resistance R. And so the equivalent resistance here is 4R. For 4 in parallel, it's going to be REQ is R over 4. And then for 1 in series, but then there's 3 in parallel. Right, so these are like the first 3 combinations that I kind of gave everyone. And this one I left for you guys to calculate REQ. And of course to calculate all the other REQs. So there's 10 in total. And try to come up with a bunch of them yourselves and then discuss with your partners here, you know, some of the ones that you can't figure out what you're missing, just they can help you out with that. So that's like the group activity part here. So everybody helps each other come up with all 10 of those combinations and then calculate those REQs. Okay?
Yeah, I got it. Thank you.
I'm gonna go to the next group now. Do you need a second to copy this down?
I got it.
Okay. And this is, which room is this? Room 3. Okay, so 4. Hello. So where do we stand here? Are we having trouble, or we get what's going on? Andrea, Yazan, Phoebe.
I get it. I'm just trying to figure out more combinations.
Okay. How many do you have so far?
I have 6.
Okay. An easy way to kind of try and come up with new ones is to take one that you already have and then just like move one resistor to like another branch, and then usually you end up creating a new one that you don't have. Once you get like 8 of them, then like getting the last 2 is a bit of a challenge. You have to really look at each kind of diagram you have, and then think to yourself, okay, I need one where it's series with 2 in parallel with 1 in series. You have to think of it like that and kind of just go through the different permutations. So it actually helps to order the resistor combinations. Yazan, how are you doing?
Struggling a little bit.
Mm-hmm.
Yeah.
How many do you have?
Nothing so far.
Do you have the first 3 that I wrote down for the problem?
To be honest, not, Professor.
Okay, can you see what I'm sharing?
Yeah, I see what you're saying. Yeah.
Let me get you started here on it, okay?
Okay.
So you're not missing out. So the idea is we have 4 identical resistors.
Okay.
And we connect them 10 different combinations of series and parallel. So 10 combinations. And we calculate REQ for each of those configurations. So here's one configuration here, 4 in series. What's the equivalent resistance going to be in this case? So we have 4 in series. For series resistors, right, REQ is equal to, right, like R1 plus R2 plus R3 plus R4. But we can just get rid of those subscripts. They're all identical resistors, right? So it's R plus R plus R plus R. So 4R, right?
Yeah.
Follow me on that? Okay. What's the next easiest one? If we got 4 in series, we could do 4 in parallel, right?
Right.
So we could jot down 4 here like this. So this is 4 in parallel. So again, R, 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 and R. And REQ here for this case, for parallel resistors, we want to sum up the reciprocals. So it's 1 over R plus 1 over R plus 1 over R, right? 4 of them.
Right.
So we get a factor of 4 over R. 4 over R. And so when we reciprocate that, REQ is equal to R over 4. And so parallel combination always makes the resistance go down. Questions about that, or that makes sense?
No, it looks clear. Yeah.
Okay. And then the third one that I gave was, so suppose I have kind of this like 4 in parallel here, but I take one of them off and just like move it to the side. So I take this one off and I put it right here. And then I do the same, kind of thing with like 3 in parallel this time instead of all 4 of them. And so this would be a new combination. It's not 4 in series, it's not 4 in parallel, it's like 1 in series with 3 in parallel. And so each one of these, again, they're all the same resistors, they're all identical. And now you have to apply the same rules to calculate REQ. So I'll just get you started here on this one. So I have 3 in parallel here. I know that if I have resistors in parallel like this, like up here with the 4 in parallel, if they're identical, if I have 4 of them in parallel, it's going to be R over 4. So if I have 3 of them in parallel, like here, what's it going to be?
R over 3.
R over 3. Okay, so that's just that part though, and so I should probably be a little bit more clear here. So this part is R over 3, but I have it in series with this guy here, right?
Mm-hmm.
So it's R plus R over 3. So that's going to give us like 3 over 3, so 4/3 R for REQ.
I see.
So just go through and do that for each of those 10 combinations, and you guys can work together on this. So talk through the different combinations. Andrea said she already has 6 of them, so feel free to share your combinations with each other. So Yazin, are you feeling better now since your incident?
Yeah, actually, that day I got in 2 accidents, to be honest.
Oh wow.
Yeah, one by myself and the other one with my uncle.
Oh wow, that sucks.
Yeah, the one with my uncle is the worst one because the hit was in my side, like the passenger side. That's why, yeah, like still like my back and my neck kind of itchy, you know. But getting better.
That's good. Just let me know if you need some extra extensions or anything. Okay.
Okay, no problem.
All right, Phoebe, you're last here, so catch me up where you are.
So far I have like 7 combinations, including the 3 that you did write down.
Okay, so you're missing a couple.
Yeah.
Are you organized in how you're approaching the problem? It usually helps a little bit.
I did label the resistors from 1 through 4.
No. I mean, like, so start with like 4 in series, and then do like 3 in series, but connected with 1 in parallel.
Oh yeah.
Like kind of keep it organized in that way. So like 2 now, like this. Let me give you guys a little bit of a hint. There's 2 combinations here that are identical, but you can write them down in a way that they're not looking identical. So, and that would be this combination here. So we have 2 in parallel like this, and that is in series with another set of 2 in parallel, like so. That combination of 2 in parallel in series with 2 in parallel is identical to 2 in series, which is in parallel with another 2 in series. So these 2 are identical. They should have the same equivalent resistance.
So are these 2 different combinations, the one that you just drew?
Yeah, these are 2 different combinations, but really they're actually identical.
Oh, okay. Okay, got it.
Okay, so if there are no questions, I'll go ahead and move to the next room.
Thank you, Professor.
Thank you.
Okay, so I'll go ahead and move to the next room. Hello. Any questions here? Oh, hold on a second. I have a notification. I think somebody left the Zoom call. Give me 1 second. I'll come back. Okay. This is room 5, right? Yeah. Jiho, can you hear me?
Yeah.
Brandon. Oh, Brandon is also disconnected, it seems. So you need me to reassign you, right? So what room were you in?
I was in with Brandon.
Oh, you 2 were together. Okay,
Yeah.
let me assign you.
Oh, sorry, I'm back. I lagged out of the meeting.
Yeah, I'll assign you back into that same room. Room 1.
Alright, cool.
So you should have it now. Go ahead and join. Room 5. Okay, I'm back. What's our progress in here, guys? Are we helping each other out?
Yeah, we're able to figure out all 10 of them.
You've got all 10 of them.
Mm-hmm.
Awesome. And that goes for Kareem and Jonathan as well.
I got most of them. I have like 7 right now.
Mhm.
So like combinations, you mean like unique combinations, right? So like you know how number 3 is you cannot do like the reverse of it, right?
Like
swapping,
no.
the combination. Okay, yeah.
Yeah.
Because I did that, I'm like, wait, you get more than that, right? So okay, yeah.
Yeah, because those ones are identical.
Yeah.
There are 2 which are identical. I'll show you guys which ones those are right now. In theory, they would be different, but actually it turns out they're the same. And that would be a set of 2 resistors in parallel, but they're connected in series. So 2 in parallel, in series with 2 in parallel. This combination is identical to 2 in series, which is in parallel with another 2 in series. So from a drawing standpoint, these are clearly different, right? However, in practice, they are identical. How about Kareem? Where do you stand on this stuff, Kareem? Has he spoken, or he's? Oh, are you there?
Yes, Professor.
Okay. Go ahead. So where do you stand on this this problem here?
Actually,
You need me to help you get started on some of this?
yeah.
Okay. Let me know. Like, so what's the confusion point?
So, so my problem is I haven't still studied yet. So I'm still facing a lot of difficulties, but I should be starting around today.
Okay, that's no problem. We can do this exercise even without this material from this chapter, because we already covered it in the last chapter.
Okay.
So try to fall back on what you remember about series and parallel resistors. I'll just remind you here. So we have 4 identical resistors. So this is just for this example here. So we have 10 combinations. The idea is to figure out all 10 of them. I gave you guys 3, and then I just gave you 2 more, right?
Okay.
So 10 combinations. And then you want to figure out what REQ is equal to, right? And you just remember that for resistors in series, we have R1 plus R2 plus R3 and so forth, right?
Oh, yes.
And then for resistors in parallel, we have sum the reciprocals, 1 over R1 plus 1 over R2 plus ... right?
Exactly.
And so the idea is to just get some practice with circuits which have like multiple of these combinations. So the easiest one that I gave at the beginning was 4 in series, right? They're identical resistors, so they'll all have the same resistance, R. So this one, REQ would be what?
Would be R1 plus R2 plus R3 plus R4.
Yeah, so that would be, if they're all R, it would be
4R.
4R, right? And then if you had them all in parallel, you had them all in parallel like this, do we know what it would be, or?
It would be 4 over R.
1 over REQ would be 4 over R, that's right. But what would REQ be?
So it would be.
So we would reciprocate both sides.
So R, it should be. Hold on.
I think you know it.
It
just
should
have
be
some.
R over 4.
Yeah, I was going to say, I think you know it. Just have some confidence there. It's R over 4. So we just flip flop this guy, right? And we flip flop this guy. So R over 4 there for that one. And then the other one I gave was just an example. How do I create these combinations, right? Where's the starting point? Well, start with something like these 4 in parallel here. and just move one to the side so that you have one in series with now 3 in parallel, right? You're limited to 4 resistors, right? So there's a limited number of combinations you can have. So again, they're all identical, but this has a new equivalent resistance. And I'll just go ahead and work through this one with you just because you need a little bit of a warm up here. So if I have 3 of these guys in parallel, what's my equivalent resistance? 4 in parallel gives me R over 4. So what would 3 in parallel give me?
So 3, it would be all over 3.
R over 3, right.
Plus,
And
plus
then
plus the resistor that's on the left, right?
Right. So then it's R plus R over 3. And then, of course, you got common denominator type of thing, right? And you get 4/3 R, right?
Right.
And so that's the idea. So the next thing you could do is you could take another one of these resistors and put it on the side. So it's like R in series with R, and then that's in series with 2 R's, which are in parallel.
Mm-hmm.
And then that's just kind of how you build up those combinations. So just go like that. So this would be like your next one here.
And then we can do 2 parallel series as well, yeah?
Right.
So 2 parallel series it would, oh yeah, okay, I got it.
Got it. And help each other out. So if you get a little bit stuck, you guys can help each other out, okay?
Okay.
Okay, I'm going to go to the next room now if there are no other questions. Okay.
Thank you.
Uh-huh. Hello. How are we doing here?
Are we allowed to like switch the orientation and count it as one different combination?
No. So if you have, so I think what you're talking about is doing the following. So if I have something like this, then this is exactly the same as having it like this. Those are the same, so those don't count.
Okay.
There are 2 which are identical in practice, but you can draw them differently. I'll give you guys those 2 now. So if I take 2 resistors and connect them in parallel, and then I take the next 2 resistors and connect them in parallel, but I connect those 2 parallel connections in series with each other, then this happens to have identical properties, namely equivalent resistance, to taking 2 resistors, connecting them in series, and then connecting that in parallel with 2 more in series. So these 2 right here are 2 different combinations, but they have identical equivalent resistance. Did you guys happen to have these ones already?
Yeah.
Okay. So how many combinations do we have here?
I got 6 more.
6 more. So you're missing like the last one.
Yeah.
Okay. Yeah, so it's always tricky with the last one because you're trying to figure out which one, you don't want to make one that's identical to one you already have, right? Jaime, where are you at? How many do you have?
I want to say I found the other 7 because I kind of noticed there was kind of like a pattern of some sort.
Yeah. Henry, maybe the one that you're missing is the following one. So or do you have this one already?
I missed that.
That's one you're missing?
Yeah.
It's a tricky one. The other one people tend to miss is the following one. So That's the other one people tend to miss. So you guys are good here, yeah?
Yep. Yep.
You guys both have this one, right?
Yeah.
Okay. I'm gonna go to the next group. I skipped a group on accident. Hello? You guys have any questions? Where do we stand here? How many combinations do we have? How about Diaz? You can go first. How many combinations do you have?
I found about like 7.
7? Is that 7 in total, right? So you're missing 3 of them?
Yeah.
Okay. How about Bernal? Can you tell me how many you have?
I was a little confused, so I barely have like 2 or 3, but the other one helped me like understand it.
Okay.
I'm still writing them.
All right. So yeah, let me, maybe I can help. I'll pull up a whiteboard here. There's 2 combinations which are identical, but you can draw them in a way it's clear that they're not identical. And that is the following. If I take 2 resistors and I connect them in parallel like this, so 2 in parallel, and I take a copy of this, so I take 2 more in parallel, so that I've used up all 4 of my resistors. This right here is 2 resistors in parallel with 2 resistors in parallel. 2 resistors in parallel in series with 2 resistors in parallel. This happens to be identical with 2 resistors in series in parallel with 2 resistors in series. So these 2 right here are identical, but we count this as one, like this is 2 combinations. Okay, so 10 combinations in total. Here's 2 of them right here, plus the 3 that I gave at the beginning. So you have already 5 of the 10 possibilities. Are we having any difficulty calculating REQ, or are we pretty good on REQ?
Yeah, I think the equations are a little simpler.
Okay. And then Bernal, how about you?
It was kind of confusing with the parallel because it's 1 over, and like the series is just add. So I was like a little, but it's easy to understand. I understand it now.
Yeah, you just have to like get used to it because you start learning it for capacitors and then you have to learn it for resistors, right? So remember, if you have 2, you can do REQ for parallel is going to be R1, R2 over R1 plus R2. But if all of these are R, right? If all of these are R, then what you end up with is R squared over 2R. And a power of R cancels, you end up with R over 2. So if you just have 2 in parallel, you get R over 2, right? So just 2 in parallel, you get R over 2. Does that help a little bit?
Yeah.
Yes.
Let me give you guys one of the harder combinations to figure out, or at least it seems like one of the harder ones. I take a resistor here and I put it in parallel with a resistor and another little parallel combination right here. So this one is a little bit tricky, but basically the idea is we have 1 in parallel with the other 3, but the other 3 are kind of in this weird combination here. So 1 in series with 2 in parallel. So did you guys happen to have this one or no?
No, I don't have that one.
Diaz, you said you did or didn't?
No, I didn't have that one.
Okay, cool. So you both got a new one then. That's good. And then maybe I'll give one more. Let's go ahead and take a look at if we had 3 in parallel here like this. But what I gave you last time was I put one right here, right? So that it was in series with those. What if I take it and I add it into this branch right here? So now it's like you got 3 branches here in the circuit, But you have 2 resistors in this branch here and just 1 resistor in these ones. So did you guys have that one?
No, I didn't have that one. Would the bottom branch be in series but in parallel?
Yeah.
Okay.
Good. So I gave you guys 2 more. That's good. All right. I'm going to go ahead and check in on other groups.
Okay.
Oh, how are we doing here? Brandon, you there? Jiho, you there?
Hello.
Okay, how are we doing?
I think I'm good.
Yeah.
How many combinations do we have?
I think I have like 8. Yeah. We're working on it.
And G, how many do you have?
Around 8 or 9. I'm working on the 9th one right now.
Let me try and get you guys some more here so we can finish this off. Do you guys have this one?
Yeah.
G, do you have this one?
Yeah.
Okay. How about this one? This is the most challenging one to come up with. So basically like this.
I don't have that one.
Yeah, no, I don't.
Okay, there you go. What would be the other one? Well, there's 2 identical ones. I don't know if I talked to you guys about this one yet, but there's 2 that are identical, and that's 2 in parallel connected in series with 2 in parallel. And this happens to be identical to the following. So we count these as 2 combinations here. So this one and this one. Those, we count that as 2 combinations, but those are identical. So 2 in parallel in series with 2 in parallel is the same as 2 in series in parallel with 2 in series.
Does this apply like as a general rule, or is it kind of just only for this setup?
It's not a general rule. It's only when all the R values are identical.
I see. Okay.
So did you guys have both of those?
I had the first one, but not the second one.
Okay. So Brandon, how many do you have left then? Do you have all 10?
Yeah, I got them.
Okay, and then G?
I think I have them all too.
Okay, you have all of them now? Okay,
Yeah.
perfect. So that means you guys are almost done then. That's good. Any questions for me about calculating REQ?
No.
Okay, so I'll move on to the next group.
All right, cool. Thanks.
Yep.
I don't know.
Hello.
Hello.
Professor.
Yes.
Okay. I was gonna actually tell you about something really quick. About the pre-lecture. Is it possible to have more questions based on the equations and concepts?
Well, I try to, yeah.
Because like I think I really like when or at least in the pre-lecture I really like the questions that kind of guide you through the equations and the questions that ask you about the concepts, because though I don't know, for this pre-lecture.
So this one wasn't that good in terms of kind of the simple guided problems.
Yeah, because for me, I think I really like when it's simple, like it kind of explains how the equations work, and because that when we get to lecture with you, then when you're showing us more in depth, we know like, hey, we just use this equation. I know what he's talking about.
I'll make a note of that, because I don't always fully check the assignments. So sometimes things like that happen. So just make sure that the PL tutorials
is like
more guided practice.
Yeah, a bit more simple. But I do like the concept question. Like there's some that where you have to make like checks or where you choose multiple answers. And I really like those because that is concept, like, hey,
they make you think, huh?
Yeah. But like I don't know, the one that where I asked you about about the resistance and the wire. Like I understand it had to do with the sum of all. I think it was what the sum of all resistors or the sum of all. Like I would like a question like that, but kind of guide me with it, because then like it's pretty much like the homework where I have to know the equation, but since it's pre-lecture, I don't really know the equation, so I don't know what it's asking me to do.
Okay, got it. I'll double check the problems next time, and then maybe if I come across one like that, I'll just put it on the homework instead.
Oh yeah, like that would have been a great homework question. But that's what I was kind of talking about too with Hillary. Just like I just think that the pre-lecture should be like something to introduce you to the chapter. That way, when we come to lecture, we have an idea what it's going on. We understand what equations you're using, and then
yeah, that's what I'm trying to do. But I know it's a miss sometimes.
yeah.
Okay, so let's get back on track here with this problem, though. So, what are our combinations that we have? Do we have all 10 of them?
Well, I'll let Hillary talk because I've been talking a lot.
So for me, I feel like I only have 8 combinations.
Okay.
I have 10, but then I get the same equivalent resistance, so I'm unsure if those count.
So this one here,
Mm-hmm.
2 in parallel in series with 2 in parallel is identical to 2 in series in parallel with 2 in series. So these two are identical, but they count as 2 different combinations.
Because so even if I get this,
so these are definitely 2 different combinations, right? So it's 2 in parallel in series with 2 in parallel, and this is 2 in series in parallel with 2 in series. But we count these, so this is 2 combinations.
Got it.
And probably the most difficult one for students to find is the following. It looks like this. So it's essentially 1 in parallel with the other 3. But the other 3 have like this weird combination inside that branch there. So it's 1 in series with 2 in parallel. And then those 3 are in parallel with 1. So did you guys get this one?
Yeah, that one I remember from pre-lecture actually.
Oh, okay, good. So then the only other like ones I could think of maybe that you might be missing are maybe one like this, where you have 2 in series in parallel with 1, in parallel with the third one, or the fourth one, I mean. You have this one?
Oh, I don't have that one. Okay,
so there's 1. Do you have 3 in series in parallel with 1?
3, yes, yeah.
Okay.
Well, how do you do that one, Professor? 3 in series and
3.
Yeah. So write.
Oh, wait.
Write 3 in series like this, and then just like put the fourth one here, right, and then just connect them.
I actually had a question about one that I had, Professor, where I have kind of 3 in series. I have 3 in series, and then I have one vertical, if that makes sense. So the 3 are horizontally in series, and then at the end, I have a resistor that is vertical.
That sounds like it's the same as 4 in series.
So it's kind of like, it kind of looks like a hammer. If that's what I was trying to explain the.
Like this?
No, more like at the end, like if you made a square, but at the very end there's a resistor. So like that, and then you make a line of series of resistors, if that makes sense. I think I could draw it for you, Professor, if that's possible.
Go ahead. It sounds like it's probably a combination that you could draw in a simpler way. But yeah, if you can draw it, then I can give you more specific.
I think there. So does that? So pretty much I have a resistor here, resistor here.
Okay, I see it.
And then one right here.
Yeah, this is that last resistor there is shorted out. So this is not a valid combination here.
Oh, it's shorted out?
Yeah, I mean, so if you connect the resistor back into the same point here, then it doesn't contribute to anything.
Oh, okay. So pretty much it's like having three.
Yeah, so like if I connected a battery here to this point here and this point here, that resistor there wouldn't do anything because it's connected. Both its terminals are connected to the same potential,
Oh, okay.
right? So
So then that well, that one gets ruled out then, yeah. Well, I did have one that is kind of like this. I saw in the homework at least one that is like this.
let me clear this, okay?
Yeah.
Go ahead.
And I have another one here, and then like this. So it's kind of these two aren't parallel, and then
Okay,
these two aren't
first
parallel.
off, when you draw these problems, put two dots for yourself.
Okay, okay.
And then if you can't draw it in between the two dots, then it's not valid.
So like that?
Yeah, so what you have here now is 3 in series, like this, in parallel with 1.
But why wouldn't because if they're directly across from each other, why wouldn't it be parallel?
Because this, and this are in series.
Oh, so it's not like this one would be in parallel and then these two would be in, so it's okay.
No, that would be a violation of Kirchhoff's laws. So you have to pick a starting point and go around the circuit and return to the starting point. So you can clearly see when you apply Kirchhoff's laws that these 3 are in series before this one is ever seen. Right? So,
Yeah. Okay. Okay. Yeah. I think those are the only ones I had then. So that wouldn't be considered a combination.
no, that's not a valid. Well, no, sorry. That's this one right here. That's the same as this.
So yeah, that's the thing, Professor. If the thing I don't get is if we're supposed to find combinations, wouldn't many of them reciprocate each other or replicate?
So there are combinations which are kind of like inverses of each other. So yeah, obviously if I take this and I mirror it, that doesn't count. That's not a combination. That's literally the same thing. I just flipped it upside down, right?
Yeah.
So this doesn't count. But the inversion of this counts. So this is 3 in series with 1 in parallel. So I could think of 3 in parallel with 1 in series, right? So 3 in parallel, that's one I already gave you guys. 3 in parallel with 1 in series. So these guys are like inverses of each other.
So Professor, pretty much we have to find 5, and then we can inverse.
Kind of, yeah, kind of. There's like a tricky one I gave you guys earlier that's kind of difficult to figure out.
Okay, then yeah, I'm gonna try again, but that's way easier. So I'll try
Help each
to.
other out, please. So like share, because I don't want to work on this one exercise for like a really long time. So help each other out, okay? So Orpho, you can ask Hillary for what am I missing, and Andrew. I haven't even heard from Andrew yet. Andrew, can you just let me know where you're at on this problem?
I have 10.
You have all 10. Okay, so Hillary and Andrew both have 10. So why don't you guys help Orphil out to figure out which ones he's missing? So that way we don't, so we can progress, right? Because there's still a bunch more sections in this chapter we have to cover.
Yeah, okay, for sure.
All right, I'm going to go check on the next group now.
Thank you, Professor.
You guys are welcome. Okay, so everybody here, I take it, is kind of finished with everything, right?
I believe so, yeah.
Okay, so I'm just going to keep checking in on the other groups. I'm going to try and get them done soon, so that way we can progress here. Hey, are you guys done with your exercise, or still working?
Yeah.
Done or still working?
Oh, I'm just working on the equations now.
Okay, and then Bernal also?
Yeah, working.
Okay, still working. Okay. Do you guys have any questions?
Not really.
Okay. Excuse me. Hey, so where are we at now?
Oh, I thought we got all of them.
You got all of them with REQ as well?
Yeah.
Oh.
Okay, so go ahead and leave the breakout room.
Okay.
So a lot of people who are done have left the room already, so they're sitting in the big conference, and then we have one group left.
All right, cool.
Hey, Professor.
Okay, I'm back. So where are we at now?
Okay, we got all of them. Yeah.
Got all of them. Okay, good. So do you now calculate REQ? Have you done that yet, or you need to work on that some more?
I mean,
a little bit more.
I think a little bit more, but I mean, I think that would actually be quicker, right?
That is a little bit quicker, yeah. Do you guys want to? So this is the last group, so I don't mean to like rush you guys, but would you guys be okay if you calculate them like after class or something, or
Yeah.
you want me to show you how to calculate them? Because I could just help you guys through it, so it's a little bit quicker. Or you guys maybe could just do it after class.
When we go back or when we separate the groups, are you gonna go over them or?
No, I'm not.
Okay, then at least for me, I think I'll just go over it after class to get understanding, but it's up to what everyone else wants.
Yeah, so that's what I'd like to do so we could keep going with the class, because we've been working on this one exercise, I think, for maybe like 20 minutes or so, maybe a little bit longer now. But it's a good exercise. So let's go ahead and let's end the breakout rooms and everybody just go join the main call, okay?
Okay, sounds good.
Okay, so we're gonna continue to progress now. So let me go ahead and share back into Paint. We can see here what we had before here. So now that we've completed our exercise here, I hope that we all feel pretty comfortable with using those combination equations, replacing resistors with equivalent resistance. Now, just keep in mind that everything that you've done here, you've done for when all of the resistors are identical, right? So all the resistance values are equal to R. They're all the same. And so some of the analysis that we've done here doesn't apply, just in general to any problem that you happen to come across on a homework or in the book. So just be careful. A lot of the things that you've learned from doing these problems, though, you may be able to apply in certain problems, right? So if you notice a certain combination where like 3 of the resistors or maybe 4 of the resistors are the same, then you can just apply that rule that you've already figured out from this exercise. Okay, so let's go ahead and move forward now. So the next thing that we'll do is Kirchhoff's laws. Okay. We've talked about Kirchhoff's laws quite a bit already. So what we're going to really do here is just apply them. And I will show you guys. So this will be one of those times where I will actually do an example for you guys here from the book. So I'm going to put up an example problem here and I'll work through it myself. And then maybe I can give a second example for you guys to work on. Okay. So this is something we've kind of already used in practice here. But let's go ahead and see how I would approach a problem. So Kirchhoff's laws, we're going to have a circuit here, which is a series circuit. So only one loop here for this circuit, but we're going to have multiple sources of EMF, in other words, electromotive force. Okay. Now, electromotive force is what we use to describe an ideal voltage source. So perhaps you think of a battery as something that has an ideal voltage source on the inside, but then it also has some sort of internal resistance which increases over time as the battery dies, right? We all know we've all had to change the batteries in, you know, a remote control or something for the TV, right? Or some toy maybe as a kid. We all know that batteries eventually die off, and that is modeled as the internal resistance of the battery increasing over time until it gets to the point where there just isn't enough juice left in the battery. In other words, enough chemical potential energy left in the battery to keep current flowing in the circuit. Okay, so here we have an example where we're looking at two batteries in the circuit here. Here we have a live battery, in other words, a battery that has a lot of juice left, a lot of potential energy still stored in the battery. Oh, sorry, not live battery. And we'll just abbreviate battery here as BATT. And then down here we have the dead battery. And we have some values here given for the EMFs of the two sources, the two batteries, and the resistance values for the resistors here. So we have a 3 ohm resistor, a 7 ohm resistor, and then the internal resistances here of these two batteries. Notice that the live battery has an internal resistance of 2 ohms, whereas the dead battery has an internal resistance of 4 ohms. The live battery has an EMF of 12 volts, and the dead battery here has an EMF of 4 volts. Okay. Now, what are we after in this problem here? Well, let's go ahead and read the problem. So we're looking at a single loop circuit here. The circuit shown in the figure contains two batteries, each with an EMF and an internal resistance and two resistors. Find A, the current in the circuit, B, the potential difference VAB, and A and B are these points labeled here, so we'll label this B and we'll label this A here. So the potential difference VAB, and part C, the power output of the EMF of each battery. So power output for those two EMF sources. All right, so how do we approach a problem like this? Well, first we label a current. And it doesn't matter how you label the current. Suppose I label the current flowing in this direction. Okay, so it flows around like this, counterclockwise. This is just my guess as to the direction of the current here. It doesn't matter if I've guessed correct or incorrect. Once I solve for the current, I will get a positive answer or I will get a negative answer. And typically we say the direction of flow for the current is the flow of positive charge. And so if I get a positive number, then that means I've chosen the correct direction for the current. If I get a negative number, that's okay. That just means that the direction that I chose is the direction of flow for negative charge. It does not change the mathematics and it will not change any of the physics of the problem. So if you're ever doing a problem using Kirchhoff's laws and you happen to label a current in a certain way and you calculate a negative answer, don't panic, leave it as is, change nothing, okay? You've gotten a negative answer, it's just a sign. It does not change the physics at all, okay? So in this case, the reason I've chosen the current in this direction is because I know that this live battery is going to supply current to charge up this dead battery, so the current has to be flowing in this direction. That just comes from experience though. You just label a current in any direction and solve the problem when you're first learning. I will now start at the point B and apply KVL. So let's go ahead and maybe label the point here. So the point B there, I am going to go around in this direction here and apply KVL. I know you guys like color here in the lecture, so we've got some yellow going on here. I know yellow might be a little bit hard to see, but I'm just going to go ahead and use it there to outline the path. I'll put the dot, and then we're back to black here. So KVL on that yellow path there. What do we do? Well, KVL says that we should sum up all of the potential gains and drops along a closed loop. And once we sum up all of those potential gains and drops, we should set that equation equal to 0. Okay, so I see there's a chat here. Yellow is easy to see. Yeah, it might be easy for you, but maybe somebody else it's not as easy to see. So I do want to avoid using yellow. So sum the potential gains and drops. What does it mean? Well, I start over here at the point B, and I look at this source that I come across here, this 12-volt source, and I recognize, okay, negative, the low potential is here on this side, and the high potential is here on this side. Well, if I'm going from low to high potential, then that means I should add. So plus 12 volts. Now, when I come across this resistor here, I've chosen a direction for the current. And since I've chosen a direction for the current, then that means I know the polarity of the voltage on the resistor. The current flows from high potential to low potential across a resistor. So since the current is flowing in this direction here, counterclockwise, so from right to left, the high potential on the resistor is on the right, and the low potential is on the left. So I subtract I times the value of the resistance there, which is 2. So subtract 2 times I. Okay, so 2 ohms times the current in amperes. So that is also voltage. And then I come across, after I pass this first 2 ohm resistor, I come across this 3 ohm resistor now. And of course, the current is flowing in the same direction here. These guys are in series. And so the polarity is like this. The current flows from high to low across the resistor. So at the high end of the resistor is the positive, and at the low end is the minus there. Or I probably should say the plus is on top, since the current is flowing from the top to the bottom. So on top we have the plus, on bottom we have the minus. So we write that in again using Ohm's law. So it's minus the 3 ohms times whatever the current is in amperes. That gives us the voltage drop there. So minus 3 times I. And then we come across the dead battery here. And again, the current flows from high to low. So it's plus on the left side of the resistor and minus on the right side of the resistor. So that is going to again be a minus 4 times I. Okay. But then something interesting happens. Now we have a voltage source where the high potential is encountered first, and then the low potential is encountered. So as we move from left to right, we cross from the high potential side of the dead battery to the low potential side of the dead battery. Whenever we go from plus to minus, that's just a minus sign. So we subtract 4 volts in this case. We subtract 4 volts, okay? And then finally we come around to the 7 ohm resistor, and again we see plus minus in this orientation, so high potential on the bottom, low potential on top, because the current flows from the bottom to the top. So we have minus 7 times I. And we've finally returned to the point B here, and so we should set this equation equals to 0. And then we can begin to combine like terms for this equation. We notice, I'll underline in orange here, these terms have a common factor of I. And these terms here in brown are voltages. These are just numbers with units of volts, so we can combine those. So in brown here, we have 8 volts. And in orange here, we have, what is that, minus 16I. And of course, this whole thing equals 0. Maybe we go back to the blue here. But this tells us, of course, what the current I is. So I will now just solve for I. Outright, it's going to be 8 over 16 with units of amps. 8 over 16 is a fancy way of saying 1/2 or 0.5. And that's how we solve for the current there. So that is the answer to part A of this question. What is the current in the circuit? Okay, so 500 milliamps, half an amp, 8/16 of an amp, 0.5 amps. Any of those answers are acceptable. I will make one note here for you guys. It is important when you solve these problems that you keep exact answers. So I have written a decimal answer here, 0.5 amps, but that is still an exact answer. If I were to find, for example, something like 1/3 of an amp, then I might be tempted to write that as 0.33 amps. But if I later have to use that current to calculate something, that may introduce some error into my calculations. So remember to use exact answers as much as possible, okay? Especially when doing these Kirchhoff's law problems, solving these circuit problems. Okay, so just a little side note there. The second part of this example, part B, is to calculate the potential difference VAB. So the potential difference VAB, this is VA here. Let me not use red, I already used red, so let's use green. So this is VA at this point here, and this is VB at this point here, okay? So if I want to calculate VAB, that's VA minus VB. Okay, so what is VA minus VB? Well, if I apply Kirchhoff's voltage law on a strange looking loop, okay, let me draw a strange looking loop here. So now we're looking at the green path here. So I'm going to do a path which looks like this, okay, and it's not broken there. So we come around like this, and we've gotten from the point B to the point A, but then what I want to do is I want to close the loop here in the space between all these circuit elements. Can I do that? Yes, of course I can do that, as long as I apply Kirchhoff's voltage law correctly, okay? And since I want VA minus VB, the potential gains as I go this way would be equal to the potential across VAB here. Okay, so VAB is equal to the gain of the 12 volts right here. We cross this 12 volt battery here. And then we cross the 2 ohm resistor, so minus 2 times I. Well, I is 1/2, right? 1/2 an amp. So this number really is just minus 1. But let's keep going here. Then we're going to have minus 3 times I, right? Minus 3 times I. And then, well, we've gotten to this point here that we're interested in knowing the potential difference across, right? So if I go from the point A to the point B, then that's like subtracting VAB. So let me just make this crystal clear here that we're applying this correctly. Let me just get rid of this here. Let's put this off to the side. Let's bring this up here. And this right here, this VA minus VB is the same as VAB. So VAB equals VA minus VB. So if I get to the point A here and I cross from A to B, that's like saying minus VAB. And then this thing has to be equal to 0, okay? So this thing has to be equal to 0 here. So now you can see I could add VAB to the other side, right? I could add VAB to the other side. Add this guy over so that we have VAB is equal to 12 minus, it's 2 times a half, 1/2 an amp, and then minus 3 times 1/2 an amp. Of course, we can punch the numbers on this. So 12 minus 1 is 11. And then we have 11 minus 3/2 is 9.5 volts. I'll let you guys run through the arithmetic there on that. It's good practice to make sure you can do stuff like that. Just some arithmetic there in your head. So we get for VAB, we get 9.5 volts there. So this little bit here of calculating VAB can be a little bit tricky, recognizing that you can draw a path like this where you're not actually on the circuit anymore. You're just kind of crossing through the circuit. As long as you do KVL on a closed loop, it does not matter where you do that closed loop. In fact, I could just create an orange path over here where I'm just doing KVL over here. I'm just doing KVL off, oh, whoops, that wouldn't be KVL. I'm just doing KVL off over here in some random area outside of the circuit. Well, there's no voltage gains or voltage drops here, so this equation amounts to 0 equals 0, and it's not helpful, right? But if we want to know VA minus VB, then we can draw this kind of a path here where we cut through the circuit and connect the point, connect from the point A to the point B, and then we assume, of course, that there is a potential difference there. There's a potential at A, there's a potential at B. And so if I want VA minus VB, I should go from A to B and assume that that's a drop, okay? So I've dropped from A to B there to get VA minus VB, okay? So that's the idea there. And that answers part B of our question there. So does anybody have any questions for me at this stage? Give me a thumbs up if you're okay to keep going.
I do have a small question, Professor. So, say we went from, is it actually possible to go from VA to VB? Because I think we were going from VB to VA. Is that right?
No. I went counterclockwise here, so I did go from VA to VB.
VA to VB?
See right here? My arrow is pointing from A to B.
Oh, okay. So would there be can you do were you able to do a reciprocal of this? Like,
could I go backwards? Yeah, exactly. Yes, I could, 100%. So I could go the other way, and the only difference between those two equations is all of the terms here would have a different sign. So if I went the other way, but notice it's equal to 0, right? So I can multiply this equation by -1. So what I would have gotten if I went the way you're suggesting, so the opposite direction, I would have had a minus 12 volts plus 2i plus 3i and then plus VAB. And that would have been equal to 0. So I could have just multiplied by a minus sign and now I have the same equation.
Okay. So that's why you said it doesn't matter which way you go.
No, it doesn't. It never matters which way you go as long as you apply KVL correctly.
Okay.
All right, so we'll go on to part 3 now, if there are no questions here. So part 3 was asking the power output of the EMF of each battery, okay? So power output. So as you guys know, or should know from the last chapter, power in circuits, we come up with this expression of current times voltage, right? So current times potential difference. Now, how do we get there? Let me just give you a quick rundown how we get there. So we start with work the amount of work that's required to move a small charge dq through a potential difference is given in terms of dq, because it's a small charge, and that charge moves across a potential difference, delta v. Okay? Forget about the sign here for a second. So we're not going to account for the sign. So if this is the case, then I know that if I have a current is dq by dt. It's the amount of charge which passes through a cross section of a wire, for example, in an amount of time dt. So I can rearrange this equation as I dt is equal to dq. And so I can substitute that in for dq. So I dt times delta v. And this is dw. But of course, we know that power is an amount of work or energy transferred per unit time. So if I divide that dt over to the left side, then I have power. And that leaves me with I times delta v. Right? So that's a simple derivation there for the power either dissipated or supplied for circuits. Okay, where we have currents and voltages. All right, so the thing that maybe is a little bit tricky is when do you have power supplied versus power dissipated? Okay, and it all has to do with the following. Suppose I have an element of a circuit here. So this is just any element in a circuit. Doesn't matter if it's a resistor, if it's an inductor, if it's a capacitor, if it's a voltage source, it doesn't matter what it is. This is some element in my circuit. Okay. If the potential difference has this polarity here, and the current is flowing in this direction, then power is greater than 0, and energy is dissipated. This is just a convention that we establish for power balance in a circuit. In other words, energy conservation in a circuit. So if an element has a current flowing from high potential to low potential across any element, then the power is dissipated, and we write the power as a positive number. If I have this situation, but the current is flowing in the opposite direction, I'll use another color here just to really make it stand out that the current is what's different here. If the current flows in the opposite direction, then the power is negative and energy is supplied. Okay, so this is just a convention. And the reason we establish this convention, and this is usually not something that's talked about in physics books, but it's talked about in circuits books. This convention, of course, it's related to conservation of energy. So really you can infer this from conservation of energy, but this allows us to establish what's called power balance for a circuit. And that is that the sum of all powers dissipated or supplied in a circuit is equal to 0. Okay, so all supplied and dissipated powers so those of you who are electrical engineers, this is the stuff you want to know. So all supplied and dissipated powers in a circuit. Okay. And this equation is sign sensitive, right? So we can't add up a bunch of positive numbers and get 0. So sign sensitive. How do I figure out the sign? Well, I just told you that's this information over here on the right. Okay, so that's power balance. Now, back to the example, we want to calculate the power output of the EMF of each battery. So we have two sources of EMF in the circuit. So I think I've given you enough time to copy this down, so I'm going to scroll up now. So here is the two EMF sources. I'll maybe pick another color here. So let's do like the pink here, and maybe I'll put like a circle around them just so it's clear what I'm talking about here. So there's that one, and there's that one. Okay. Notice that in the top circuit, in the top part of the circuit, the current is flowing from low potential to high potential across the EMF source. Okay. So the current in the top part of the circuit is flowing from right to left. That means that the EMF source at the top is supplying power to the circuit. If you look at the EMF source at the bottom of the circuit, the current is flowing from left to right. In other words, it's flowing against the potential that that EMF source at the bottom has. So it's flowing from high to low. That's against what the battery wants. Normally a battery wants to supply the current from low to high. And so the EMF source at the bottom part of the circuit is actually dissipating power. In other words, it's absorbing power that's being supplied to it from the live battery. So you can start to connect these ideas in your head now. The battery at the top is a live battery, and you've connected it to this dead battery at the bottom. So it makes sense that the live battery supplies power, while the battery at the bottom, the dead battery, dissipates power. In other words, it absorbs power. Okay. And of course, some of the power that that battery absorbs is dissipated by the resistor as well, the internal resistance. And some of the power supplied by that top battery is dissipated by its internal resistance as well, the 2 ohm resistor. Okay. And so we can calculate now the power for the 12 volt. And that power should be negative according to our convention. Since power is being supplied, the current flows across the terminal of the EMF from low to high. We insert the minus sign by hand into our expression for I times, well, rather it's half an amp, right? So 1/2 an amp. And then the voltage, the EMF is supplying 12 volts, so that's 12 volts there. And we get -6 watts for the power. So an amp times a volt, you can work it out for yourself. It's the same as a watt. And so this is our answer for the live battery. So 6 watts supplied. So it's minus by the 12 volt live battery. Then of course we have the 4 volt dead battery. This is positive, it is dissipating power. It is absorbing some of that energy being supplied by the live battery. And that of course has the same current flowing through it, but the voltage is different here. And so we end up with a positive 2 watts. So 2 watts is dissipated, in other words, positive power, by the 4 volt dead battery. Okay. And that completes this example. However, there's more that we can do here with this example. We don't have to stop there. We could now begin to ask the question, well, what about the power balance? Is power balanced in this circuit? How much energy is supplied by the, how much power is being supplied by the live battery as a whole, right? So the live battery has some of the power that it's supplying dissipated by its internal resistance. So now I will ask you guys to finish this example off by calculating the following thing. So now this is an example for you guys to work on. So example, so calculate the power supplied or dissipated by all of the elements in the circuit does power balance hold? For part A, does the power balance hold? For part B, what is the total power supplied by the live battery? So that includes the internal resistance of the live battery. And then part C, what is the total power dissipated by the dead battery, right? So again, that includes the internal resistance of the dead battery. Okay, so there's the three-part example for you guys to work on. It's exactly the same circuit that you have already. It's the same exact circuit. You just need to calculate the power for each of those resistors. Now, quick little reminder: if you combine the fact that power is I times delta V with the fact that delta V equals I times R for a resistor, then you can rewrite the expression for the power dissipated by a resistor as I squared times R, or, well, equals, so or, delta V squared divided by R. So only for a resistor. Only for a resistor can you do this, right? Because it has R in the expression. Okay? So go ahead and work on this example here. And maybe what we'll do is, again, I'll give you guys 10 minutes to work on this example. And if you finish it early, then you can have a longer break. If it takes you a little bit longer, then you'll end up with a slightly shorter break. But that's how we'll do it again. So it's 4 o'clock. So we'll meet back again at 4:10 p.m. And go ahead and put your answers into the chat so you can compare with your fellow students. Okay. Any questions before we begin?
Yes. So you said in part B and C, the total power supplied by the live battery. Then what is the P12 volts and the P4 volts that you wrote up top?
Those are the powers that are supplied by the ideal EMF sources inside of the battery.
Oh,
It does not account for the fact that the battery has an internal resistance.
oh, okay.
So and you would just add. So you would take that negative number and add into it the positive power dissipated by the internal resistance.
Okay, got it.
Okay. Any other questions? All right, so we'll meet back here in 10 minutes. So 4:10. We can go 4:11. That's fine too. Okay, I'm back. I don't see anybody putting any answers in the chat yet, so I'm wondering if there's some hang up here on this stuff. We already have the current. We have a bunch of resistors, so getting the power dissipated by those resistors should be straightforward, I squared times R. So is there some confusion here? Or just people were really eager to to go use the restroom?
Just go back from the bathroom. So it's starting to do it now.
Oh, wow. Okay. So people are maybe a little bit behind here on this one. I don't want to give extra time to go through this problem because it's a fairly straightforward problem. It's a fairly easy problem. Let me outline the solution for you guys because the next topic is going to require extra attention, the RC circuit, which is a more challenging topic. So I want to make sure that you can ask questions about this harder topic. Then if not only is it going to take a while to get through the RC circuit, it's also, I want to give some time for questions. So let me outline the solution to this problem now. So if I want to calculate the power supplied or dissipated for each of the elements, well, the first thing I can recognize is that resistor always dissipates power. So resistors always dissipate power. So those are all going to be positive. Okay, so the power dissipated by the 2 ohm is going to be 2 times a half squared. Right, so let me write that in I squared times R fashion. So 1/2 squared times R, which is 2, and that's going to give us, of course, 1/2 a watt. Power for the 4 ohm. There was a 4 ohm, right? Yeah, there's the 4 ohm there. The 4 ohm is going to be 1/2 squared times 4, right? This is going to be a 1 watt power dissipation. We have the 3 ohm and the 7 ohm. 3 ohm is going to be 3/4. And then the 7 ohm is going to be 7/4. Okay, I see a chat. Yeah, that's what I did. Good job. That is correct. And then once you have these, now you have all the powers in the circuit because you also have that the power, the 12 volt is -6 watts, if I remember correctly, -6. And we have the power of the 4 volt is positive. It's dissipating power, even though it's an EMF source, positive 2 watts. Right, and so if I add all of these up, I should end up with power balance, and I can already see that just quickly calculating in my head here. I can see that these total 4 watts, and so power balance is achieved here. Sum of the powers is equal to 0, so power balance is achieved. Okay, now I will zoom back in for you guys in a second here. Let me just give myself some more space. Okay, so power balance is achieved. Excuse me. Now the second part is, what is the total power supplied by the live battery? Okay, well, part B. So it's going to be the power of the 12 volt plus the power of the 2 ohm. Okay, so what does that equal? That's your answer. Part C, what is the total power dissipated by the dead battery? Well, the dead battery is the 4 volt EMF and its internal resistance, which was 4 ohms. So what is that plus that there? Power of the 4 watt plus power of the 4 ohm. And when you add those up, those are your answers there. So this is the power supplied by the live battery. And this is the power dissipated by the dead battery, if I can spell dead correctly. Okay, any questions about that? Give me a thumbs up if you're ready. We're going to go on to RC circuits now. Okay, so I will now demonstrate for you guys how to eat healthy. Okay, here's a carrot. and we'll do the RC circuit now. So RC circuit is quite challenging because it requires knowledge of differential equations. However, the RC circuit only requires knowledge of solving first order differential equations, which is a topic covered in your Calculus 1 class. So suppose I have a battery connected to a capacitor. Well, a battery is modeled as an EMF source with some sort of internal resistance. And then your capacitor, of course, has capacitance C. And so this is the best you can do if you ever connect a capacitor to some sort of voltage source. You have to include for the fact that that voltage source has some sort of internal resistance, or that your wires have some sort of resistance, right? No matter how small it is, it's not going to be zero. So R cannot be zero. There has to always be some kind of resistance, okay? All right, so what do we do in a situation like this? Well, the only thing we can do is apply Kirchhoff's voltage law. If we suppose, and I'll try and use the same color here, that the current flows in this direction, then we know the polarities on each of these devices here. So, of course, the EMF source has this polarity, positive at the top, negative at the bottom. The resistor would then have polarity like this, plus minus in this fashion. And then the capacitor, of course, same type of thing there. The top plate would be high potential, the bottom plate would be low potential. The top plate would charge up with a positive charge, and the bottom plate would charge up with a negative charge. Okay. However, when a capacitor becomes fully charged, it's fully charged. No more charge flows in the circuit. And so when the capacitor becomes fully charged, the current must go to zero in this loop. And so that tells us right away that the current must be a function of time. Okay? And if the current is a function of time and the capacitor is charging up over time, then the voltage on the capacitor is a function of time, and the voltage on the resistor is also a function of time. Okay, so we have delta VR of t, and we have delta VC of t. Okay. Whenever we set up a problem like this, we need to have some sort of initial condition. We could start with the simplest initial condition, and that is that the capacitor is uncharged. If the capacitor is uncharged, then that means at time t equals 0, the voltage across the plates of the capacitor is 0. So this implies that Q of t equals 0 is also equal to 0. And those two conditions there, that is not two initial conditions, that is one initial condition. Those two conditions there are linked by the following equation. The charge on the capacitor as a function of time is equal to the capacitance of the capacitor, which we're assuming does not change. In some cases, you could have the capacitance changing as a function of time, but not in this case. The charge on the capacitor plates as a function of time is the capacitance times the voltage as a function of time, okay? And that is specifically the voltage on the capacitor plates, which is no longer the same as the voltage supplied by the EMF source or the voltage source, because we have a resistor here, right? Since we have a resistor, then the potential difference on the resistor is equal to current times resistance by Ohm's law, right? And the potential across the capacitor is equal to Q equals C times delta V, that equation that has no name, but it's for a capacitor. And so we can now apply Kirchhoff's voltage law. Again, I'll do it in yellow because we kind of started that way last time. I'll start at a point over here and I'll go along the circuit like this until I've gone all the way around the circuit. Okay. Maybe dotted lines is not the best way to do it though. I'll just do a solid line. So we're going to go around the circuit like this. And apply KVL. So KVL around that yellow loop. How do we do it? Well, let's start with the simplest thing that we could do. KVL says sum up the voltages. So let's first start by writing down the voltages. If I start at this point over here, let's label it A. If I start at A and I cross the EMF source, obviously I pick up an amount equal to E, right? So I gain E. As a matter of fact, let's change the notation here. Let's go ahead and let's ditch E and let's put delta V. Let's go ahead and change it up here. Let's put delta V here. Okay, so that way it's clear we're looking at all the same voltages here. So I'm sorry, that we're looking at voltages here. So delta V is what I pick up. As I go from the point A, I cross the battery or the EMF source. Then I'm going to cross the resistor. Well, what's the potential difference on the resistor? It's delta V sub R. Okay, and it is a function of time, but let's leave that out for a second. And then I cross the capacitor, and the capacitor, again, the potential difference on the capacitor is delta V sub C, and it is a function of time. But let's ignore the time dependence here for a second. If this is going to be equal to 0, well, then that tells me that the potential difference across the source has to be equal to the sum of the potential difference on the two components here, like so. And it also tells me that since I have a constant on the left side, I must also have a constant on the right side of my equation. So this is constant. That means that this is also constant. And therefore, the time dependence of the voltage across the resistor must be equal and opposite to the time dependence on the voltage for the capacitor there. They're going to be the same time dependence. It has to be that way because when I sum them, I have to get a constant. So they're going to be like, it's almost like a Newton's third law type of thing. It's got to be equal and opposite so that the time dependence cancels if I add those two together. Hopefully that made sense. And you'll see that here in a second when we set up our differential equation and solve it. So now that's the next thing to do, is to use these other equations that we know. So let's go ahead and maybe write them down in red here. So delta V, well, actually I already have this one in blue, so let's go ahead and write it in blue. And that is that the potential difference across the resistor is equal to, and I'll put the function of time piece in here as well, is equal to the current as a function of time times the resistance R. And again, we assume that R doesn't change, but it is a very realistic thing to do to assume that R does change, right? Because, for example, if we're working with a light bulb is going to heat up a bunch and it's going to start glowing, right? And its resistance value will skyrocket as the current increases, right? A light bulb is the perfect example of a breakdown of Ohm's law, right? Ohm's law is a linear relationship, but we know that the resistance value increases as we increase the current for a light bulb. So here we have our two equations which we can use to replace delta V's in our equation at the bottom here, okay? And I will actually take this equation here and multiply it by a negative sign. So I'm going to go ahead and take this equation and multiply it by a minus sign. And I'm going to write it over here. The first term I want to write down is the delta V sub R. So in terms of the current here, that's I of t times R. And R is the constant, so I'll put R on the left side. Okay, so that's delta V sub R. The next term I want to write down is the potential difference across the capacitor. And let me scroll up a little bit so we can see the equation again. So if I want to solve for delta V sub C, then I need to do Q of t over C. So we'll write it as 1 over C times Q of t. And that is delta V of C. And then finally, I have minus delta V, and delta V is a constant. This equation is equal to 0. Okay? But now we need to recall that the current I of t is a derivative of the charge. Now, we're used to writing dq dt with a little q, but little q and big Q here must be the same by Kirchhoff's current law. So all the current that goes, that flows in the circuit, some of that current charges up the capacitor, and the rate at which the capacitor is charged is going to be the same as the rate of decrease of the current, and so forth. So we'll write this as dq of t here, capital Q. It's the same as the little q that we're used to working with. We've just labeled it differently in this case. Okay, so dq dt is the current flow in this circuit. And you can already guess that eventually it must go to 0 when the capacitor is fully charged.
Professor,
Go ahead.
just so I understand, when we have t, does that mean, say we have 5 seconds, would you multiply this by 5?
No, these are functions of time.
Okay. So how would you use the t in here?
So if I have a function of x, and that function is, let's say, x squared plus 1, if x is 5, then that means not f times 5, but it means f of 5. So I plug in 5 like this. Does that make sense?
Yes.
Okay. So we're not multiplying by t here. We're writing an equation in terms of functions of time. Okay. So what do we do next? Well, we plug in for I. We plug I as the derivative of q. And now we have a differential equation here, which we need to solve. Okay. Divide this equation by r and move some of these terms to the other side, so that we have dq of t by dt is equal to, and how do we want to do this here? I think this this should be fine. So no, let's leave everything on the same side here. So 1 over RC Q of t minus delta V. Actually, we probably should move the delta V to the other side, because we can do this by integration factor. Okay, so that's what we'll do. We'll move the delta V to the other side. Okay. And now what we want to do is, and I'm not going to go through like a full-on rigorous solution to this equation, because obviously not everybody here has taken differential equations or maybe even remembers how to handle these first order equations. This is not an equation that we can just integrate both sides and be done with it. And so what I'll do here is I'll use a method of just kind of guessing an answer, but with good reason. So everybody who's taken calculus knows there's this function e to the x, right? So f of x is equal to e to the x. And the derivative of this function, df dx, is again the exponential function, right? So the derivative of the function is equal to the function. And so that's kind of what we got going on over here. We have a derivative and we have the function itself, and we have to be able to add those together to get a constant, right? So if we are to add two functions of time and they add together and end up giving us a constant, then they better be of the same form as a function. And that form will have to be the exponential function, because the exponential function is the only function whose derivative is equal to the function itself. So only function where derivative equals the function itself. Okay. And so what we can do is we can guess a solution of that form. And that's a standard technique in differential equations that you'll learn more about, when you take that class, right? So for us here, we'll try to not get too deep into the math, but I'll try to go as deep as we need to really understand the problem here. So just let me know if I need to further explain something so that it makes a little bit more sense. What I want to do now is I want to write down a guess for q of t. And I know it has to look something like an exponential function. And perhaps maybe it has, well, let's see here. So let's make a careful guess here. So in this particular problem, what is the charge doing? Well, the charge starts off at 0, right? That's our initial condition. If the charge starts off at 0, then it's got to climb up to a maximum value, right? Once it climbs up to that maximum value, then it's got to stop climbing, right? And so what kind of behavior should we guess here? Well, we could say that an exponential, well, obviously the exponential depends on t, right? This exponential here has to shut itself off as t gets really big, okay? So if t gets really big, that means t going to infinity. How do we shut off the exponential? Well, you put a minus sign in the exponent. If I take the limit as t goes to infinity here, then what happens is this exponential becomes 0, right? And when the exponential becomes 0, then we should reach a maximum amount of charge. Okay, so when this exponential becomes 0, we need to reach a maximum amount of charge. Okay, what about the initial condition? When t is 0, this thing is 1, right? Well, we don't want that. We want the charge to be 1. Sorry, excuse me. We want the charge to be 0 at t equals 0, right? So we better subtract this off somehow, okay? We better subtract this off somehow. So we better say 1 minus this thing. Let's take a look at this function now. So if I plug in t equals 0, then I have 1 minus e to the 0. That's 1, right? If t equals 0, this thing is 1. So we have 0. That works. Okay. Now, what about if I take the limit as t goes to infinity? So if I take the limit as t goes to infinity, then I have 1 minus, and then e to the minus infinity. What's e to the minus infinity? Well, that's
Would
1
it be
over.
0?
Oh, go ahead. Yeah, it's 0. It's 0. So it goes away. So the limit as t goes to infinity, we get the answer 1. Okay, well, that's not exactly what we're looking for. We're looking for the maximum charge on this thing, right? So let's multiply by that. Let's multiply this thing by the maximum charge. Oops. So I'll take this thing and I'll multiply by the maximum charge. What's the maximum charge going to be? Well, the maximum charge is going to be given in terms of the maximum potential difference and the capacitance of the capacitor. But we can just leave that there for now, right? We just leave that there for now. We need to do one more thing here. I have a t in my exponential. I can't have t in my exponential. Why? T has units of seconds, okay? Since t has units of seconds, I have to make this thing unitless. I have to divide by some other quantity which has units of seconds. Otherwise, my units will not work out correctly. I'll have e to some units, which makes no sense, okay? And so I have to put in this parameter tau, which has units of seconds. And so I hope that now I've convinced you that this function has to have this form here. It's the max charge, which gives us the units of charge, times some function here, 1 minus an exponential, where it has the limiting behavior that we want to see, okay? And now we can figure out what some of these things should be from the
Professor,
equation. Oh, go ahead, yeah.
do you think you can explain what the Q max and the tau is for again?
Q max gives us the units so that it has units of charge. And also, if we take the limit as t goes to infinity, this term becomes 0, like you pointed out. And that means we have Q max times 1. So in the limit as t goes to infinity, Q of t equals Q max, which is exactly what we're looking for.
And why are we looking for Q max exactly?
When the capacitor is fully charged, right? After a long time, the capacitor will be fully charged. And so that would be the maximum amount of charge on the capacitor.
Oh, okay. That makes sense.
Okay, so with this information now, we can check what some of these parameters that we kind of fudged in there actually are. So that's what we're going to do now. So in the limit as t goes to infinity, the capacitor will be fully charged, okay? That means the current flow in the circuit will be 0. So let me go ahead and take the limit here on this equation as t goes to infinity. The current must go to 0 as t goes to infinity, right? Because when the capacitor is fully charged, then no more current is going to flow in the circuit. So that term is 0 when I take the limit. Now, when I take the limit on Q of t, that's what we've called Q max, right? But let's leave the time dependence in there for a second. Okay, let's leave the time dependence in there for a second and see what happens here. Nothing happens to the constant term on the right side. So we have 1 over RC Q of t. I guess, technically, I guess we could just write, the Q max here if we want to. But what's going on here? Something. Did I forget? Oh, that's what happened. Okay. Sorry, guys. I remember I was a little bit confused there because earlier I divided the equation by R, but actually there's a mistake here. Do you guys see the mistake? I only divided this term by r here. I forgot to divide this term by r as well. So we need to fix that in our notes. So delta V should also be divided by r.
Professor.
Yes.
I thought when you said you divided r, I thought the r gets canceled because isn't the r the first thing you divide over to 0? So 0 divided by r is just 0.
But look, we have these two terms here, right? We have these two terms here, so they both need to be divided by r.
Right. Okay. I see that.
So now that because I was getting confused myself there for a second because the r's weren't going to cancel, but I know the r's should cancel here. So, let's go ahead. Actually, let's go ahead and replace just real quick. Actually, so we will replace q of t with q max since we're taking the limit here. Let's just go ahead and do it. That's going to be delta v over r, and what we see is r's cancel on both sides, and we see that q max is equal to, in the limit, C times delta V. And delta V here is the source voltage, not the voltage. Well, it is the same as the voltage across the capacitor plates, but it is also now in terms of the source voltage. So in the limiting case, as t goes to infinity, the potential difference across the capacitor plates is the same as the potential difference across the terminals of the source. Okay, so it's an application there of the equation Q equals C times delta V in the limit. Okay, now how about that parameter tau? What is that tau there? Well, we can figure tau out by taking a derivative. Let's take a derivative of this equation. So dq of t, let's actually write it in the red here. dq of t over dt. And actually we're a little bit over time here, so let me kind of speed things up a little bit so that we don't go too far over. If I take a derivative of the 1 here, I get 0. So I'm taking the derivative of just the right side of the expression. Okay, so we have q of t is equal to q max times 1 minus e to the minus t over tau. And so for my derivative of q, I have minus q max over tau e to the minus t over tau, right? And oh, sorry, and actually there's a double minus here. There's a double minus, so it comes out to plus. So there's 1 minus here, and then there's 1 minus here from the chain rule. Okay, and so what is tau here? Well, this is the current flow in the circuit, right? So this is I of t. This is I of t, right? So this should add to 1 over RC times Q of t. So Q max, this is I over tau, e to the minus t over tau, should add to 1 over RC times Q of t, and Q of t is Q max times 1 minus e to the minus t over tau, and then that has to be equal to delta V. So this is what we talked about. We have to be able to add the current and the charge with the appropriate constants, and then the time dependence has to cancel so that we get a constant. Okay, and now you should be able to read off what tau is. Look, here's tau right here, and this thing right here, Q max e to the minus t over tau, is the same as this thing right here, right? And so this RC must be equal to tau. So tau must be equal to R times C. And if that is the case, then what we're left with, oh, sorry, it should be delta V over R. I did it again. Divide that by R. Divide that delta V by R there. So now we can see that the time dependence pieces will cancel. So this term, because it has a minus sign, will cancel with this term here. The time dependences will cancel out. And what we'll be left with is Q max over RC is equal to delta V over R. So exactly what we had before, which just tells us again that Q max is equal to C times delta V. And so everything checks out there. If tau is equal to RC, then everything is good. So we have a name for tau, it's called the time constant. And you can check that units of resistance times units of capacitance really do come out to units of seconds. Kind of interesting that that happens, but it does. Okay, so it has units of seconds. Okay, and so now we actually have a valid solution for our differential equation. We've proven now, we first guessed the properties that Q of t must have. And by doing that guess, we've figured out that the charge can be written down as a function. You could put Q max or you could put C times delta V. It doesn't matter what you put. Is 1 minus e to the minus t over RC, or you could leave the tau there. That's fine too if you want to just leave the tau. That's the charge as a function of time as it builds up on the capacitor. And again, you can check t equals 0 and you can check t going to infinity so that it becomes fully charged. The derivative gives the current, and we can see that again. I can write this down as I max. I'll let you figure out what I max is. E to the minus t over tau. And we can see that at t equals 0, we have maximum current. That's when the capacitor is not charged. Remember, it's easy to charge up the capacitor when there's no charge on the plates. But when there's more charge on the plates, there's more of a repulsive force, so it requires more energy. So the current decreases as a function of time to 0. Well, the voltage across the plates of the capacitor is also a function of time, right? And it's given as Q of t divided by C, right? And so we can write the voltage as a function of time as delta V 1 minus e to the negative t over RC. That's the voltage on the capacitor as a function of time. What's the voltage on the resistor as a function of time? Well, we'd apply Ohm's law, right? So Ohm's law says I of t times R. Well, what's I? I is just given right here. So I max times R is going to be the same as delta V. I'll let you prove that for yourself. Delta V and then times e to the minus t over tau. And that's the voltage as a function of time across the resistor. Since the current is a maximum at t equals 0, the potential difference across the resistor is a maximum initially in the circuit as well. And that is literally everything that we can write down for this circuit here, okay? That's literally everything that we can write down. We now have the voltages as a function of time, we have the current as a function of time, we have the charge on the plates of the capacitor as a function of time, and that's everything, right? There's nothing else we can really write down for this circuit. There is one more circuit I want to talk to you guys about before I let you go, okay? And that is a discharging capacitor. So that's kind of the opposite of what we had there. A discharging capacitor is when we start with a maximum amount of charge here. So it starts with a capacitance C and a maximum charge Q on it. We'll call it Q0 for the initial charge. And we have this resistance here, R. I'll let you check this, follow the procedure from before. Notice there's no voltage source here. If you add in a voltage source, that's the same thing as saying the capacitor has a little bit of charge. So its charge is not 0 when we first start, and then it charges up to its maximum. What we're looking at here is a discharge of a capacitor. So there is no voltage source. And so the capacitor has some charge on it. And because it has some charge on it, it will generate some current across the resistor. Okay, so in this case, the charge as a function of time for the capacitor is going to be in terms of Q0, so the initial charge, and the charge has to decrease as a function of time. So it's going to be Q0 e to the minus t over tau. I take a derivative of this thing, right, and I see that, of course, if the charge is not being driven by a voltage source, then the current must also decrease over time. And of course, there is no delta V being supplied to the circuit. So when I write the current, I write it as Q0 over tau, or you could write it as Q0 over RC. Okay, and so the current initially begins at a maximum value and then decreases to 0. Again, I'm leaving this for you guys to check on your own. Delta V C of t, this of course is given by Q of t divided by C again, and so it's exactly the same kind of thing as before, so Q0 over C e to the minus t over tau. Notice everything in this case when we have a discharging capacitor and a single resistor here, with no voltage source, everything decreases over time, right? Because this capacitor stores up some energy and then it supplies that energy to the resistor. And that's the end of the story, right? Eventually all of the energy is gone. Of course, the potential difference across the resistor has to be the same as the potential difference across the capacitor, because these two elements here are connected in parallel. They are in fact connected in both parallel and series in this case when you just have two elements, right? They're both parallel and series. So this of course is, you can write it down in terms of Ohm's law. So I of t times R. And so you could write that as Q0 over tau times R e to the minus t over tau. But of course, you know that tau is R times C. So you could cancel the tau and the R and just leave a C in the denominator. And that again is the end of the story. That is both of the potential differences as a function of time, the current as a function of time, and the charge as a function of time for a discharging capacitor. So let me go ahead and stop. Well, actually, maybe one more thing. One more thing, remember that power is current times potential difference, okay? And so if I have functions of time here and I want to know the total amount of energy dissipated, I have to integrate power as a function of time. And if I want to know the total amount for the lifetime of the circuit, then I should integrate from 0 to infinity. So if I want to know the total amount of energy supplied by the capacitor, for example, in the discharging case, well, the maximum amount of energy stored in a capacitor is going to be 1/2 Q squared over C, right? And so if I were to integrate, and you guys check this for yourself, the energy dissipated by the resistor, check that the value, sorry, it should be Q0 squared over here. So this is some constant, right? We know this. Check that the energy dissipated by the resistor, if I integrate from 0 to infinity of I of t delta V of t dt, check that I actually get that value there. Does this actually give me that constant? It should, right? Energy should be conserved. So does anybody have any questions about that? I know that was, we went quite a bit over. Sorry about that.
I did have a question. How often are we going to use these equations that you just gave us? Like,
what do you mean by how often? I mean, it's like a check, right? So you can check that energy is conserved by calculating the total amount of energy that's stored here in the capacitor, right? That's the only amount of energy that you have in this problem.
mm-hmm.
And then over time, that energy is dissipated by the resistor. And so we should be able to calculate the power dissipated by the resistor. So for example, you could also write it as I squared times R, right?
Right.
And integrate I squared. And you should be able to integrate for all times, right? Because the capacitor is only at charge equals 0 when t goes to infinity. So you have to integrate from your initial time to your final time. Your initial time is t equals 0. Your final time is t goes to infinity, right? It's an improper integral.
So, Professor, would E equal the integral from 0 to infinity pt? Does that mean that the E is always getting bigger? Because I'm assuming in this integral the P is a constant, so you could just pull that out, and the integral of
No. P is a function of time, right? So all of these functions are so all these guys depend on time, right? So the current as a function of time times the potential difference across the resistor, that's also a function of time. So the power is I times delta V, right? So these are functions of time.
So then, if you did the integral of P, would you just get PT?
So I have to take this function here and multiply it by this function. That's P.
Oh, okay. Dang. So then when you're doing the integral, you have to, dang, that's a lot.
It's really not. It's just an exponential function, right? So the integral of an exponential is an exponential, right? So when you take the limit, the upper limit, it's going to go to 0, right? E to the
yeah, that's what we just.
Yeah, e to the minus.
Yeah, that's what
it's
we
really
just
not
did.
a lot.
Yeah.
It's really not a lot. You're just
Okay.
maybe you're tricking yourself into thinking it's harder than it is. It's pretty simple.
Yeah. Okay, then then never mind. Yeah, that's easy.
Any other questions? All right, let's end it there then. Let me know if you guys have any questions regarding the homework. Somebody pointed out to me that when I put up the homework part 2, I put it on Thursday again. So I moved that over to Friday for you guys.
Oh, Professor.
Yeah.
Did you ever do something about the office hours? Like, were you able to?
Yeah. So like right now, I'm willing to answer questions for office hours right now. So let me go ahead and stop the recording. So this is finished.